Use the graph of y equals sine theta below to sketch the graphs of the following modifications. In the previous video, we discussed amplitude and period quite extensively. We're going to keep on with that. We also talked about vertical translation. The part we didn't get to is phase shift, and that'll be towards the end of the video. So we have the graph of sine looking at us, and that is two oscillations of the sine curve. We use the unit circle to generate values for angles and y coordinates that coincide with the sine function. Let's look at the example here. 3 times the sine of 1/2 theta. Our amplitude is the absolute value of the lead coefficient, which in this case is 3. The period is 2 pi divided by the coefficient of our angle. And since that's theta over 2, that's 1/2. 2 pi divided by 1/2 is 4 pi. So this oscillates only at half the speed as normal, because a normal sine curve takes 2 pi units to get a cycle done. This one takes 4 pi. So it takes twice as long to get there, and that's because of the 1/2 coefficient. The sine curve typically has a hill followed by a valley in its cycle. Now, since this graph paper runs out at 2 pi, we can only get half the cycle. We only get that hill. If this x-axis went all the way out to 4 pi, then the next 2 pi units would be our valley. So we only get half an oscillation where we would normally get a full oscillation. So a fraction that's less than 1 in front of your angle slows down the oscillations. A number larger than 1, like 2 theta or 3 theta, speeds up the oscillations. We also discussed the cosine curve. A brief example would be -4 cosine of 2 theta. The amplitude is absolute value of -4, which is 4. And that'll take our peaks and valleys from 1 and -1 to 4 and -4. It's a vertical stretch. 2 theta means that we get 2 oscillations in the time it normally takes 1. It oscillates twice as fast, meaning it only takes half the distance to get there. So we will run a full oscillation in only half the time. The negative in the lead coefficient means that we're going to flip this graph upside down or reflect it across the x-axis. So let's see how that plays out. Okay, the amplitude of 4 takes us to peaks and valleys at 4 and -4. The graph needs to be flipped upside down and only run half the speed as normal. Now this graph you're looking at is the cosine curve without the reflection. So I'm going to take a bright color like yellow and sketch this in. It would be upside down and that would be 1 oscillation at pi. The -4 as a lead coefficient tells us to flip. So this would be your graph, the one in yellow. On this next slide, we're going to jump back to the sine function. Its generic graph is given at the top. We discussed vertical translations. This one you have to be very careful. This is a +2 minus 1 sine theta. The negative sine theta is the graph of sine flipped upside down or reflected across the x-axis. It still has an amplitude of 1 because the absolute value of -1 is 1. The period is normal. That's 2 pi divided by an unwritten 1 in front of theta. So that's 2 pi. So nothing has changed about the vertical stretch or horizontal stretch or compression, either way. What is different is a reflection across the x-axis. So the graph will need to be drawn upside down, but also shifted up because that's a positive 2 units. Let's see if that's what happens. The sine curve is normally a hill followed by a valley, but because it's upside down, we had to sketch it with a valley followed by a hill. The vertical translation of 2 just tells us that all function values have been added to 2, and then the result gives you what's called kind of a new x-axis. It's a new symmetry. But the main thing to remember is if you have a negative coefficient attached to your trig function, the graph will be upside down. Now we're going to do a few where we have phase shift. We're going to look at the basic cosine curve, and we're going to take the function cosine of 2 theta minus pi. Now we still have a lead coefficient of 1, so the amplitude is 1. The period is 2 pi divided by the coefficient of your angle. 2 pi over 2 is 1 pi. That tells us that the graph only takes pi units to go through one cycle. And then now we have this extra term in the angle, and that results in a horizontal shift called phase shift. If you take 2 theta minus pi and set it equal to 0, when you isolate your angle, theta, you get pi over 2. Pi over 2 will be the starting angle for your graph, for one cycle of your graph. So we're going to start at pi over 2. Where do we end? If you add pi to it, you get 3 pi over 2. The phase shift is the start, phase shift plus period is the end, and then we hit all the key spots in between. Here's our graph. The amplitude is 1. Now, I've kind of stretched them so that we'd have more room to play in here where I had to do some writing, but we're still going to peak at 1, minimum at -1, and return to our maximum. Phase shift tells you where the cycle starts. That was pi over 2. If you add the period, pi over 2 plus pi, that's 3 pi over 2. That's the angle where your oscillation stops. And so you start, maintain your amplitude correctly, and then you stop after a distance of pi has been traveled. Let's do another one with phase shift. We're going to take a sine curve, and we're going to introduce a new function, y equals 2 sine of theta plus pi. This lead coefficient, the absolute value of 2 is 2. That's our amplitude. So that tells us our new max and min values will be +2 and -2. The angle theta has an unwritten 1 in front. So that tells us the period will stay 2 pi. 2 pi divided by the unwritten 1. That's 2 pi. This will be the distance horizontally needed to complete one cycle. Where do we start? We have an extra term in our angle. If you take theta plus pi and set that equal to 0, then you get, over here at the bottom right, you get theta equals -pi. So we're going to start our cycle at -pi. If you add 2 pi, that takes us to +pi. That's where we will quit. Our max and mins will be at 2 and -2. And then our graph will look same shape, hill followed by valley. Let's take a look at it. There we go. The amplitude was 2, so our new max and mins are 2 and -2 respectively. Our phase shift was negative pi, that's where the cycle starts. The period was 2 pi, that's the horizontal distance to where your start and end happens. Negative pi plus 2 pi was positive pi, so that's where we quit. Still looks like a sine curve, it just has a new max and min and starting and stopping points. And that's basically what phase shift does, is it will translate your graph, it'll shift it horizontally, whatever you get when you set the entire angle equal to 0 and solve. In this example, when we isolated theta, we got a negative pi, so that's the starting point. I hope this video helps you out. Let me know if you have any questions. Reach out by email or phone. If we have class together, please feel free to ask in class.